Hello, in the previous clip we started our discussion on control of unstable systems, and in this clip we shall continue this discussion. So, we saw that unstable systems could possess Bode plots whose phase characteristics make it difficult for us to decide what the correct conditions are for the closed loop system to be stable. So, subsequently we found that Nyquist plot is the one plot which helps us determine whether the closed loop system is stable or not. So, we had to revise firstly the rules for determining whether a closed loop system is stable or unstable in the Nyquist plot, and then we examined the Nyquist plot for the kind of open loop gain that we considered, the unstable loop gain, and then found out for what case the closed loop system is stable. And subsequently we also discovered that there were fundamental limits to the gain crossover frequency of an unstable system. So, just as in the case of a non-minimum phase system there was an upper limit to the achievable gain crossover frequency, in the case of an unstable system there is a lower limit to the gain crossover frequency. In other words, the gain crossover frequency has to at least be a certain value for in the interest of stability in order to achieve a certain phase margin specification. If you want a certain gain margin also in addition to the specified phase margin, then the minimum gain crossover frequency necessary will be even larger. So, as a rule of thumb we noticed that the minimum gain crossover frequency necessary for the closed loop system to be stable is generally several multiples of the location or the numerical value of the unstable pole of the open loop system. So, the fact that there has to be a minimum bandwidth necessary for an unstable system has some unfortunate consequences. The first is the additional sensitivity of such systems to measurement noise. So, as we have discussed in the past, we want to minimize the bandwidth of the closed loop system so that it is able to achieve the performance specifications, but beyond that frequency range within which we are expecting performance for the closed loop system, we want the loop gain of the closed loop system to be reduced as fast as possible, but without of course jeopardizing on the stability of the closed loop system. But what we discover in case of unstable open loop systems is that the closed loop system has to have a certain minimum bandwidth no matter what the frequency range of this disturbance or reference we want to track or reject is. So, for instance, even if we are interested in rejection of disturbances or tracking of references at frequencies very close to DC or at very low frequencies, we still need to maintain the closed loop bandwidth to be more than omega Gc min. So, which was given by A tan Pm by 2, or in other words a few multiples of the location of the unstable pole. So, that is one unfortunate consequence. The second even more tricky situation arises when we are stuck with a plant which has both unstable dynamics, or in other words a right half plane pole, as well as a non-minimum phase term such as a time delay or a right half plane 0. So, in this case the right half plane 0 imposes an upper limit on the achievable gain crossover frequency, while the unstable pole imposes a lower limit on the achievable gain crossover frequency. For instance, if we consider a plant of the form P of S is equal to A minus S by S minus B times P1 of S, where the terms A and B are both greater than 0. In other words, this is a plant which has a right half plane 0 as well as a right half plane pole, unstable dynamics as well as non-minimum phase behavior, and it is assumed that the transfer function P1 of S is a minimum phase transfer function, all of its poles and zeros are on the left half of the complex plane. Then this can be written as P of S is equal to A minus S by A plus S times S plus B by S minus B times P1 of S times A plus S divided by S plus B. So, all I have done in this case is to multiply and divide the right hand side by the same expressions, namely a plus s and s plus b, and this is the expression that we get. So, we note that the first two terms correspond to the familiar Blaschke products, and then we have the other term, namely p1 of s times a plus s by s plus b. So, now we can call this part of the transfer function, namely p1 of s times a plus s by s plus b, as p minimum phase, PMP of s. So, we would therefore have that the plant P of s would be given by a minus s by a plus s times s plus b by s minus b times P minimum phase of s. Now, the Blaschke product a minus s by a plus s, as we discussed, imposes an upper limit on the achievable gain crossover frequency. In other words, if this is the frequency axis, let me call this omega, we would have omega Gc max to be equal to a cot Pm by 2. So, this is the maximum achievable gain crossover frequency for a specified phase margin Pm. If we want a certain gain margin, it is going to be even smaller than this particular value. Now, since the system has unstable dynamics, the unstable dynamics demands a certain minimum gain crossover frequency, and that is given by omega Gc min equal to b tan Pm by 2. Hence, the non-minimum phase 0 imposes an upper limit on the gain crossover frequency, the unstable pole imposes a lower limit on the gain crossover frequency, and it may or may not always be possible for us to satisfy both these specifications. For instance, if omega Gc max is less than omega Gc min, or in other words a cot Pm by 2 is less than b tan Pm by 2, what that means essentially on the frequency axis is that there is a certain frequency which we can call as omega Gc max, which is the maximum allowed frequency for us to have a certain phase margin, and we can only achieve gain crossover frequencies of magnitude less than that. Now, because we have unstable dynamics, there is a minimum gain crossover frequency necessary, and that we call omega Gc min, and we can only achieve gain crossover frequencies of value greater than or equal to omega Gc min in order for our closed loop system to be stable. Now, if these two permissible regions for the gain crossover frequency do not intersect, what it means is that it is not possible for us to have a control system, no matter what kind of controller we design, that will give us that specified phase margin Pm. So, in other words, if A by B is less than tan square Pm by 2, then we are in big trouble. It is not possible for us to design a closed loop system with a specified phase margin Pm. So, in other words, even if we have unstable dynamics and non-minimum phase 0, the location of the non-minimum phase 0 A should be much greater than the location of the unstable dynamics B in order for us to be able to design closed loop systems with respectable extents of stability. Now, you might wonder under what circumstances would we have plants which exhibit both unstable dynamics as well as possess non-minimum phase behavior. It turns out that such plants are more common than we imagine. In fact, the humble bicycle is one which is both unstable as well as exhibits non-minimum phase dynamics. In fact, the steering dynamics of a bicycle shows non-minimum phase behavior, and all of us are aware that a bicycle is an unstable system, and we have learnt it the hard way when we were trying to learn riding a bicycle. So, a bicycle is of course an unstable system, and it also exhibits non-minimum phase behavior as far as its steering is concerned. Now, one can design bicycles in such a manner that the location of the unstable pole and the non-minimum phase 0 are such that it is not possible for us to have adequately high phase margins for the closed loop system that we might want to come up with to control the bicycle. In such a case that bicycle would become an unrideable bicycle. One example of an unrideable bicycle is a bicycle which is rear steered. So I have shown here the photograph of a rear steered bicycle. So what you see is that this bicycle for all intents and purposes looks like a regular bicycle, with the exception that the steering handlebar, which is shown here, is connected to the rear wheel through this chain and sprocket arrangement here. Now you can show that if you have a rear steered bicycle, then the location of the pole and the zero of this bicycle are such that are so close to one another that we cannot get appreciable phase margins for the closed loop system, and hence our closed loop system can never be in practice can never be stabilized. So as a general rule of thumb, if the ratio between A and B, in other words if the ratio of the location of the non-minimum phase 0 and the unstable pole is less than 5, then such systems are so difficult to stabilize that it is not worth investing effort in designing controllers to stabilize such systems. Even if one were to try and attempt to stabilize such systems, it is very likely that we would have very small phase margins, and therefore there is a very real threat of instability of such systems. So as a rule of thumb, therefore, if we have a system that has both unstable dynamics as well as shows non-minimum phase behavior, then the ratio of the non-minimum phase 0 A to the unstable pole B should be significantly greater than 5. Now when we talked of the stability of this bicycle, we noticed that it was difficult to stabilize it because of the particular locations of the non-minimum phase 0 and the unstable dynamics of the bicycle. This can be remedied by reducing the location of the unstable pole. So if the unstable pole is brought closer to the origin, or in other words if the unstable pole B is made smaller in magnitude, then it is possible to achieve this ratio of A by B to be large enough for us to stabilize the bicycle, and that is precisely what has been done in this new bicycle design, which once again is a rear steered bicycle. As you can see here, the handlebars are connected to the rear wheels of the bicycle, but this time the center of gravity of the bicycle has been raised to such an extent that the location of the unstable pole is closer to the origin than for the bicycle that I showed in the previous slide, and hence for this bicycle the ratio of the non-minimum phase 0 to the unstable pole can be made large enough that we can stabilize it, and therefore we can ride this bicycle. This is also why it is possible for clowns in circus, for instance, to ride unicycles. If you have noticed the kind of unicycles that clowns in circuses ride, they are usually cycles with very tall handles, and the person who is riding it is sitting at the very top of this unicycle. Why is that so? That is so because if this person is seated that far up on the unicycle, then the location of the unstable pole is going to be closer to the origin, or in other words the unstable dynamics is going to be quite slow. It is going to take quite some time for the bicycle to flip over, and this allows the person enough time to quickly correct for any tendency on part of the unicycle to flip over. So when you are therefore trying to control unstable systems, the bandwidth or the speed of response of the actuator when we are trying to control the system has to be adequately large, and if that is not so, then it may not even be possible to control the unstable system. So as another example similar to the one that I just gave, where you had a unicycle with a very tall seat which helps the rider to balance the unicycle better, one can also think of balancing a stick on one's hand. As part of your childhood experience, you might be aware that it is easy to balance a tall stick on your hand, but significantly more difficult and sometimes even impossible to balance shorter sticks. So if I have a stick that is as short as this pen or even shorter, for example a matchstick, it is practically impossible for us to stabilize this stick. Why is that so? Fundamentally it is so because larger sticks or longer sticks have very slow unstable dynamics, and that allows us, we are the actuators in this case, our hand is the actuator, our hand's motion can be fast enough to compensate for any tendency on part of a long stick to get destabilized from its nominal position. Whereas if you have a very short stick, its dynamics is very fast, it can flip over very quickly, and our hands are not fast enough to prevent any tendency on part of a short stick from flipping over in sufficiently fast time in order for it to stay put at its nominal position. So this discussion brings us to the centrality of the bandwidth of actuators in the control of unstable systems, and sometimes if the bandwidth of the actuators is not chosen to be adequately large, it can have disastrous consequences, and on a few occasions in the recent past the importance of the bandwidth of actuation when one is trying to control an unstable system has been overlooked often even by professional controls designers. So it is well worth visiting this topic and understanding the limits of achievable performance in terms of stability, and understanding the limits of achievable stability metrics such as the phase margin and the gain margin if you are given the location of the unstable pole and if you have specified the bandwidth of the actuator that you have to control this open loop unstable system. So this analysis relies heavily on Bode sensitivity integrals, and Bode sensitivity integrals allow us to derive very simple relationships that can be used to predict the best possible phase margin and the best possible gain margin if you are given the bandwidth of your actuator and if you are told the location of your unstable pole for the plant. So let us now discuss the limits on stability imposed by unstable dynamics in the presence of actuator bandwidth limitations, and we shall do this, as I said, by using Bode sensitivity integrals. So if we revisit the control 1 degree of freedom control system that we have been looking at so far, we have a controller, and in all cases we assume that this controller was an electronic system that realized or implemented the control laws that we might choose to design. But in practice the controller can itself be looked at as a cascade of two systems. One is the electronic subsystem of the controller, which I shall call as CE, C subscript E, which might reside in a computer or which might be an electronic circuit that implements the control law that we choose to achieve, and the output of this is fed to an electromechanical element which converts some voltage input to either a displacement or a velocity change or some such or it affects the physical variables that we are trying to control, and this element, this electromechanical element, is of course called as the actuator. So we can call this as a CA. So our controller therefore is a cascade of the electronic subsystem and the actuator subsystem, and the output of the actuator of course is fed to the plant. The plant is moved by the actuator, and the output of the plant is measured by the sensor and is fed back in the interest of feedback control of the plant. So the reference is provided here. So the two blocks CE and CA put together actually form our controller. Now in most cases the electronic subsystem of the controller is very fast, is fast enough that it is not going to limit the closed loop bandwidth of our feedback control systems. This is especially true when we are controlling fairly big mechanical systems or processes in industries whose rate of change, whose dynamics is very slow compared to dynamics of electronic elements. The actuator however has limited bandwidth because it is an electromechanical device. It could be a motor, it could be a valve, it could be an element of that kind, and the bandwidth limit on the actuator in turn imposes limits on the performance of the closed loop system, and this is particularly of concern for unstable systems because there is possibility of a real accident to happen. So to understand this, let us now use Bode sensitivity integrals. We had visited Bode sensitivity integrals a few clips back in connection with the fundamental properties of the loop gain, and we had derived it in the case of minimum phase loop gains, and there we saw that the sensitivity function S satisfies this particular equation. Ln of mod of S d omega from integrated from 0 to infinity is going to be equal to 0. So this was the expression that we had for Bode sensitivity integrals in the case of minimum phase loop gains, or in other words where sensitivity function S is equal to 1 by 1 plus L, and we assume that the poles and zeros of L are all on the left half of the complex plane. Now we also talked of this integral being equal to 0 as quote unquote the law of conservation of sensitivity dirt. We called this ln of magnitude of S as sensitivity dirt because generally as feedback control engineers we want the sensitivity to be as small as possible, because if sensitivity is very small, if capital S is very small, it means that the loop gain is very large, and if loop gain is very large then we are happy as control engineers because that will allow us to reject disturbances, achieve robustness to plant parameter variations, achieve good small errors to tracking references and so on and so forth. So we want sensitivity to be very small, and hence we called it sensitivity dirt because we would like dirt around us to also be small. But then what this equation told us is that you cannot make the sensitivity dirt go away everywhere along the frequency axis. So for instance, if the x axis is omega and the y axis is ln of magnitude of S, we note that in the interest of performance we might choose to reduce the sensitivity over some frequency range. Let me call that frequency as omega naught. So below omega naught we might want to have a low sensitivity. Now what that means is that if we have reduced the sensitivity in this particular frequency range, then the exact area that we have reduced here has to be added on to the rest of the frequency range, so that we would have heightened sensitivity in the frequency range between omega naught and infinity. So we cannot make the sensitivity dirt go away everywhere along the frequency axis. If we dig a trench in a certain frequency range in the interest of improving our control performance there, then we have to pile up the sensitivity dirt at a different location along the frequency axis, so that the net area of under the curve or the net quantity of sensitivity dirt that we have dug within one frequency range is going to be equal to the net quantity of sensitivity dirt that we have added on in some other frequency range. So these two areas, if I were to call this area as A1, if I were and this area as A2, we have A1 should be equal to A2 in magnitude. Now it so happens that if we have a open loop system which exhibits unstable dynamics, so in other words if the loop gain of our system has poles on the right half of the complex plane, then the expression for the sensitivity integral gets modified somewhat. So if you have an open loop system that is unstable, then the sensitivity integral, namely ln of magnitude of S d omega, will not be 0, but instead would be equal to pi times the sum of the real parts of all the poles that are on the right half of the complex plane. So if you have k poles on the right half of the complex plane, then the Bode sensitivity integral would be equal to pi times summation from I equal to 1 to k, the real parts of the poles pi of the open loop system which are on the right half of the complex plane. So this is how the Bode sensitivity integral equation would look if you have unstable dynamics as part of your open loop system. Now in the particular case that we have been discussing so far, we have assumed that there is an unstable pole at S is equal to A. So for our particular case we would have the Bode sensitivity integral, or in the case when you have one unstable pole or one pole on the right half of the complex plane, you would have the Bode sensitivity integral to be given by integral ln of magnitude of S d omega is equal to pi times A. Now what this means is that if we dig a trench up to some frequency omega naught, or in other words if we reduce the sensitivity dirt ln of magnitude of S over some frequency range up to some frequency omega naught, then the pile of dirt that we have to add on in the rest of the frequency range, which is between frequencies omega naught and infinity, is larger in height or is larger in magnitude than the case for the minimum phase system. So the dirt pile is taller in case of the unstable system, and the total dirt that we have to have in frequency range between omega naught and infinity is larger than the dirt that we would have in case of the minimum phase system by the amount pi times A. So in this case, for instance, in the case of the unstable open loop system, we would have that A2, this new area will be equal to A2 dash equal to A1 plus pi times A. That is the total amount of dirt that we would have in the frequency range beyond omega naught. Now the question we want to answer is the following. So we unavoidably have to increase the sensitivity over some frequency range when we reduce the sensitivity over another frequency range, and the extent of increase in case of the unstable system is higher by the amount pi times A. The question is, how do we distribute the sensitivity dirt in the frequency range between omega naught and infinity? So there are two possibilities. So if I were to draw once again the ln of magnitude of S, capital S, as function of frequency, up to omega naught we are expecting feedback performance, and therefore we have dug up a pit there and reduced the sensitivity dirt in this frequency range up to omega naught. Now beyond omega naught, what do we do? Now that we have this excess dirt, namely the dirt of quantity A1 plus pi times A, how do we distribute it over the rest of the frequency range? There are two possibilities. One is we can make a tall heap of this dirt at some particular frequency. So we can basically get all this dirt to be located within some frequency range and make a tall heap of this dirt. This is one possibility. The other is we can distribute it as a thin layer over the entire frequency range from omega naught to infinity. So this is a thin layer, this is a tall heap. Now which of these two should we choose as control engineers? Should we choose to distribute this sensitivity dirt in the form of a tall heap near some frequency, or should we distribute it uniformly as a thin layer over the entire frequency range? Now to answer this question of whether to distribute it in the form of a tall heap or a thin layer, let us look at the consequences of in the first case distributing it in the form of a tall heap. So if we have a tall heap, then it means that there is some frequency omega 1 at which ln of magnitude of S is a very large number, or equivalently the magnitude of S itself is a very large number. So let me call that number as k, which is much greater than 1. So we would have that magnitude of S at j omega 1 is going to be equal to k, which is much greater than 1. Now what is the consequence of having a very large sensitivity in the neighborhood of some frequency omega 1? So we note that by definition sensitivity is given by 1 by 1 plus L, hence we would have the magnitude of 1 by 1 plus L of j omega 1 to be equal to k, which is much greater than 1, or equivalently we would have that the magnitude of 1 plus L of j omega 1 is going to be equal to 1 by k, and since k is much greater than 1, we would have that 1 by k is going to be much less than 1. Now what does it mean if we have a loop gain of such a manner, of such a kind that 1 plus L is very small, is a very small number? So to see the implication of this, let us go back to our Nyquist plot. So in the Nyquist plot we are plotting of course the real part of L versus the imaginary part of L, and we have the critical point minus 1 at this location here. So some point here in the complex plane represents the complex number L, and hence 1 plus L is represented by the complex number starting at the point minus 1 and ending at the point ending at this particular location, namely that of L of j omega. So this complex number is going to be equal to 1 plus L of j omega. Now the magnitude of 1 plus L is equal to 1 by k specifies that at the frequency omega 1 the distance of L of j omega 1 from the point minus 1 is going to be equal to 1 by k, or in other words the loop gain L of j omega 1 lies on a circle of radius 1 by k centered at the point minus 1, and if k is a very large number then this radius, so this magnitude of 1 plus L by j omega is 1 plus L of j omega is going to be equal to 1 by k. So if k is a very large number, the radius of this circle is going to be extremely small, and what that in turn means is that the loop gain L of j omega 1 will be extremely close to the critical point, and if the loop gain is extremely close to the critical point, then we know that our closed loop system is on the verge of instability, or in other words our stability margins are going to be extremely small. Now we can show that if we have the distance of our loop gain L of j omega 1 to be equal to 1 by k from the critical point, then the best achievable phase margin, which I shall call as Pm max, can be given by 2 times sine inverse of 1 by 2k. So this is the best achievable phase margin, and the best achievable gain margin Gm max is given by 20 log of k by k minus 1. So if k is a very large number, we note that our phase margin is going to be a very small number, because 2 times sine inverse of 1 by 2k will be approximately equal to simply 1 by k when k is a very large number, and therefore phase margin will be a very small number. And likewise the gain margin also will be a very small number, because when k is very large, k and k minus 1 will be very nearly equal in magnitude, and hence we would have 20 log of k by k minus 1 to be very close to 0 dB. So a very large value k is therefore synonymous with very small phase margin and very small gain margin, and the fact that our closed loop system would be on the threshold of instability. Hence if we come back to this decision that we have to take, namely whether to distribute the sensitivity dirt in the form of a tall heap or as a thin layer, the answer from this analysis is quite clear. We do not want tall heaps, because tall heaps are synonymous with low stability margins. So we want to distribute this sensitivity dirt in as thin a layer as is practically possible. Now what is the frequency range that we have available for us to distribute the sensitivity dirt? It is infinity, because we have the entire frequency range from omega naught to infinity in which to distribute this dirt of amount A1 plus pi times A. And since we have this infinite stretch of frequency in which to distribute this dirt, you might argue that we have no issues associated with its distribution, because we can distribute it as an infinitesimally thin layer over the entire frequency range. But this makes an important assumption which is not valid. If you want to distribute a sensitivity dirt as a uniform layer of infinitesimally small thickness over the entire frequency range, it means implicitly that we can control the thickness of the sensitivity dirt over the entire frequency range from omega naught to infinity. But in practice that is not the case. There will be a frequency which we shall call as capital omega A, which is decided by the bandwidth of the actuator, beyond which we cannot control the loop shape, or in other words we cannot control the way in which the sensitivity function would vary as function of frequency. So let us now rewrite the Bode sensitivity integrals taking into account this particular constraint. So we have the Bode sensitivity integral to be that integral 0 to infinity ln of magnitude of s d omega is equal to pi times a, and we can split this integral as integral 0 to omega naught ln of magnitude of s d omega plus integral omega naught to infinity ln of magnitude of s d omega, and we noted that integral 0 to omega naught ln of magnitude of s d omega, we called it as A1, and there is a negative sign because we have reduced the sensitivity to less than 0 dB in this frequency range, and the rest of it together should add up to pi times A. Now the second integral can further be split up into two integrals. One is the integral from omega naught to capital omega A, which is the bandwidth of the actuator, and that, so we would have integral from omega naught to capital omega A ln s d omega plus integral capital omega A to infinity ln of magnitude of s d omega to together comprise the integral ln of omega naught to infinity ln of magnitude of s d omega. So this minus A1 should be equal to pi times A. Now as we discussed, it is not possible for us to control the thickness of the sensitivity dirt, namely ln of magnitude of s, for frequencies beyond omega A because of actuator bandwidth limitations. So if the actuator bandwidth is only omega A, there is nothing we can do to control the shape of the loop L of j omega for frequencies beyond omega A, and hence this integral, namely omega A to infinity ln of magnitude of s d omega, is something whose value we cannot control by using whatever controller we might choose. Hence I shall call this particular term as some constant delta, which is going to be determined by the particular controller or the actuator that we choose for controlling our unstable system. So what we would have therefore is that integral omega naught to capital omega A ln of magnitude of s d omega is equal to pi A plus A1 minus delta. So we have this quantity of sensitivity dirt, namely pi A plus A1 minus delta, which has to be distributed between the frequencies omega naught and capital omega A. So let us mark that out here graphically. So the y axis is ln of magnitude of s, the x axis is linear omega. So there is a frequency omega naught, below that we have dug a trench and reduced the sensitivity dirt, and the total quantity that we have reduced is, as we discussed, A1. Now and beyond the frequency omega A, we cannot control the thickness of the sensitivity dirt, and that the integral of sensitivity dirt or the total quantity of dirt beyond the frequency omega A we called as delta. So what we have to distribute between the frequencies omega naught and capital omega A is this particular quantity pi A plus A1 minus delta. Now the question is, how do we distribute it in this frequency range? We should distribute it in such a manner that the maximum height of the pile of dirt is minimized, because if we have dirt getting piled up at any particular frequency in this frequency range, it means that we will have a larger sensitivity at that frequency, and larger sensitivity, as we discussed, is synonymous with poor gain margin and phase margin or stability specifications. So we want to distribute the dirt between these two frequencies in such a manner that the maximum height of the dirt pile is minimized. Now a moment's thought would reveal that the only way to do it is to make sure that the height of the dirt over this entire frequency range is the same, which is equal to some ln s minimum, ln of magnitude of s minimum. So this is going to be the minimum height of the dirt pile between the frequencies omega naught and omega A, and what is its value? Its value is easy to obtain, assuming that we have distributed the dirt such that it is of constant height between omega naught and omega A. So this term inside the integral is going to be constant, so we can remove it from the integral and write it as ln of s minimum times integral omega naught to omega A d omega is equal to pi times A plus A1 minus delta, or in other words ln of magnitude of s minimum is going to be equal to pi times A plus A1 minus delta divided by capital omega A minus omega naught. And this in turn can be further simplified to give us the expression that the magnitude of s minimum is going to be equal to e to the power pi times A plus A1 minus delta divided by capital omega A minus omega naught. Now this is an important expression because this expression will allow us to compute the best achievable gain margin and phase margin specifications if you are given the bandwidth of the actuator omega A and the location of the unstable pole, namely small a, the extent of benefit in terms of feedback performance we want to achieve in terms of capital A1, and the frequency range up to which you want to achieve this performance, namely the frequency omega naught. And we also have this extra term delta, which represents that integral of the sensitivity function or the sensitivity dirt for frequencies beyond capital omega A or beyond the bandwidth of the actuator. Now to see how we can put this to use, we first need to note that we would like this magnitude of S minimum to be as small as possible. The smaller it is, then the better is the phase margin and the gain margin specification. So for instance, the phase margin maximum, as we discussed, is equal to 2 times sin inverse of 1 by 2k, or in other words 2 times sin inverse of 1 by 2 times magnitude of S minimum. Likewise, the best achievable gain margin was given by 20 times log of magnitude of S minimum divided by magnitude of S minimum minus 1. So we would like to have a high gain margin and a high phase margin, which implies that our magnitude of S minimum has to be as small as possible. And this equation here, which we have obtained by using Bode sensitivity integrals, reveals the dependence of magnitude of S minimum on the different parameters of our control system. To see how we can minimize it, we note that if we stop expecting any performance whatsoever from our control system, in other words we are not really interested in performance at all, let us focus simply on stability and let us see what needs to be done to improve the stability margins of our closed loop system. If that is all that our goal is going to be, we note that we can make the frequency omega naught up to which we are expecting performance, and the quantity A1, which is what we would have in order to get the particular control performance we want, we can set them both to 0 if we are not expecting any control performance at all. If we do that, immediately we see that the term on the right hand side will reduce. So we would have therefore that if our A1 and omega naught are set equal to 0, so in other words no performance expectation, we would have that the magnitude of S minimum is going to be equal to e to the power pi a minus delta by capital omega A. Now for the sake of simplicity, I shall assume that the term delta is much less than pi a, and for this case we would have that the magnitude of S minimum is going to be this very simple expression given by e to the power pi a divided by capital omega A. So this expression will tell us what is the smallest possible value for a magnitude of S that we can achieve for a specified actuator bandwidth omega A and the specified location of the unstable pole. And if we have this information, we can plug it into the two equations that I have written here on the left and compute the best possible phase margin and gain margin specifications. So let us compute the best possible phase margin and the gain margin for some typical cases. For instance, if we choose an actuator which is just as fast as that of the unstable dynamics, or in other words if we choose an actuator whose bandwidth omega A is exactly equal to A, then we would have that the magnitude of S minimum would be equal to e to the power pi times A by A, or in other words e to the power pi, and we can show that e to the power pi is equal to 23.14. So if the magnitude of S minimum is equal to 23.14, we can use the two equations on the left top corner to calculate the best possible phase margin and the best possible gain margin. So let me write that down here. So Pm max and Gm max when we have that omega A is equal to A. So, for this particular case the best possible phase margin can be computed to be equal to 2.5 degrees and the best possible gain margin is going to be equal to 0.86 dB. So, you notice the startlingly low values of the best possible phase margin and the best possible gain margin when we choose an actuator that is exactly as fast as our unstable dynamics. Suppose however we made the mistake and chose an actuator whose bandwidth omega A was actually half of the location of the unstable pole, or in other words omega A was equal to A by 2, small a by 2, in which case we would have that the magnitude of S minimum would be equal to e to the power pi times A divided by A by 2, or in other words e to the power 2 pi. If you compute the numerical value of e to the power 2 pi, you get it to be approximately equal to 534. And if you substitute this value of 534 in the equations on the top left corner to compute the best possible phase margin and the gain margin, we find that when omega A is equal to A by 2, or in other words our actuator bandwidth is half the value of our unstable dynamics, then we would have that the best possible phase margin is going to be merely 0.1 degrees and the best possible gain margin is going to be equal to 0.04 dB. So, what this therefore reveals is that if we choose actuators whose bandwidth is comparable to the location of the unstable pole, then for all practical purposes we would have closed loop systems that are going to be unstable. There is no way we can practically achieve a feedback control system whose phase margins are going to be this small, namely 2.5 degrees or 0.1 degrees, or gain margins being that small and still manage to get stable closed loop operation. If you recollect in the past when we performed control design, we chose to have phase margins of at least 40 degrees in the interest of stability. On the other hand, with actuators that are of this particular bandwidth, namely of bandwidth comparable to the unstable pole's value, we would have phase margin and gain margin that are exceedingly smaller than the typical and the minimum values that we assumed earlier in the interest of safety of operation. So, what I also want to point out is the elegance and the power of the technique of Bode sensitivity integrals in deriving these best achievable stability specifications. If you notice this equation that has been enclosed in the black bracket, there are only 2 bits of information that we are using as far as the open loop system is concerned. We are just depending on our knowledge of the actuator bandwidth and the location of the unstable pole to quickly determine what the best achievable phase margin and gain margin specifications are. It does not matter what controller we use, it does not matter where the other plants poles and zeros are, the best achievable performance specifications almost entirely get determined by the location of the unstable pole and the bandwidth of the actuator. And if we use simple controllers, then our best achievable phase margin and gain margin will be even worse than this, because the kind of sensitivity as function of frequency that gives this particular equation here as the magnitude of S minimum is shown here in this graph on the bottom left corner, and we note that the dependence of the sensitivity on frequency is some fairly strange dependence which cannot be realized using simple controllers. Hence, if one were to use simple controllers, then the best possible phase margin and the gain margin are going to be even worse than what we have accomplished through this analysis. Unfortunately though, the importance of Bode sensitivity integrals has reduced with time to the point where professional control engineers are often not even exposed to the notion of Bode sensitivity integrals, even though these integrals are extremely powerful and help us to compute very quickly and with bare minimum information about the plant the best possible stability specifications, and this has had some disastrous consequences. For instance, what you see in this photograph is the event of an accident that happened to this particular fighter jet Gripen JAS 39. So, fighter jets are designed to be open loop unstable because it helps them with maneuverability. However, the design was done in such a manner that it was not possible for the actuators that were chosen to stabilize this open loop unstable aircraft to actually stabilize them with adequate phase margin and gain margin. Since the actuators were chosen to be rather slow and the fighter jet was designed to be open loop unstable, in the interest of improved maneuverability, we had a problem on our hands. The phase margin and the gain margin were too low, and as a result, even before this aircraft took off, the aircraft crashed and it caught fire. Fortunately though, the pilot of this aircraft escaped unhurt. So, I want to remind you again that the control system for this aircraft was designed by professional control engineers, but unfortunately though these control engineers were presumably not exposed to border sensitivity integrals and its importance when it comes to computing the best possible performance. Since people have tended to forget the significance of this result since the time that Bode first proposed this. The second example is far more tragic, and this has to do with the Chernobyl nuclear power plant meltdown. So, nuclear power plants are also unstable systems, and nuclear power plants have a water jacket that takes away the heat generated by the nuclear reaction. However, if we are not able to take away the heat fast enough, then the entire nuclear reactor can overheat and melt down. Now, this can happen if you have bubbles in the water that is used to take away the heat. If you have air bubbles or air pockets forming in the water, then the thermal conductivity of the overall liquid will get reduced because air is a bad conductor of heat, and hence the heat cannot be taken away as fast enough as one would like it to be. So, if you have a pump that cannot take away heat as fast enough, or in other words an actuator that cannot remove heat away as quickly as is necessary from a nuclear reactor, then once again we will have an unstable closed loop system on our hands, and that in this case has resulted in nuclear meltdown with disastrous consequences to the people and the animals living near it. So, people have called the Chernobyl nuclear disaster as one of the worst industrial disasters in the history of humanity, and it is a sobering thought that the blame for this disaster can be laid almost entirely at the feet of feedback control engineers, and their ignorance of the limitations of feedback control systems, especially when such control systems have to control unstable plants such as the nuclear power plant. So, it is well worth our effort to remember therefore the fundamental limitations that exist when we are trying to control certain types of plants, and the possible danger associated with controlling specially unstable plants such as a nuclear power plant or an unstable aircraft or some other such unstable system, and be aware of the tools that can be employed in order to compute the best possible performance that one can achieve if one chooses a particular actuator to control these systems. Thank you.